Today we will talk about wires, and this is going to be the eighth chapter or lecture eight um, in your slides. So, in terms of wires, whenever you have um, two gates connected to each other, obviously there is in between a wire that connects the two, and this wire um, is part it is the way that we interconnect the gates in the integrated circuit. In this lecture we will discuss how to estimate the resistance and capacitance of the wire. So we would like to add this component into our circuit analysis because um, as we know that wires impact the speed of the circuit, they impact the power of the circuit, and they impact the noise in the circuit. Okay, so these are the major impacts of interconnect. For very long wire, we will see that the delay becomes um, uh, large enough that we need to split the wire into smaller segments, okay, and use repeaters between these smaller segments, okay. So we will discuss repeaters as well in this and also finally we're going to talk about an interesting phenomena which is a skin effect. Okay, so four major topics in this lecture. Okay, so let's go back to our slides and we'll see um, in terms of the wire resistance, we see that the wire, okay, the wire um, can be looked at as um, a piece of metal with a thickness of T, length of L, width of W, and this wire is separated from the neighboring wire with a space of S. This wire is separated from the layer beneath it by a height of h. We refer to the distance between the edge of this wire to the edge of this wire as pitch. And obviously, the smaller the pitch, the better it is for designs because I can um, have more wires laid out next to each other. In the, in the old processes, the the wire width was very large. So this is the width compared to the thickness of the wire. Okay, so this is all processes. So you can see that this uh, T over W is much smaller than 1. But for modern processes, it is this ratio is more of um, something like that. Okay, so this is T and this is W. So W, T over W is about 2. And basically, fundamentally, what is happening here is that we are really shrinking the width of these wires. Again, why? Because I want to make the pitch smaller. Okay, smaller pitch means more wires, more wires. Okay, and I have more devices, more interconnects, etc. Now, the change of design from or the change of wire design from this shape to this shape have have produced different estimates for the capacitances, and we were working um, in the past with certain models for these wires, and now we have to update those models to more complex models because of this aspect ratio. Okay, all right. Now, in old processes, we used to have um, 3 metal layers or even less, and in modern processes, metal layers are more. So you can think of these metal layers as they are. If I use the probably the next slide, you can see here for 90 nanometer process, we have metal layer 1, 2, 3, 4, 5, 6. For 45 nanometer process, we have more metal layers. That's number one observation. And the thickness and the width are smaller. So I was able to cram more wire layers here in less thickness. Okay. Okay. So that's how we make ICs with more devices by miniaturizing widths and spaces. Okay. So watch the metal layers here. Metal layers that are at the top typically are wider, all right, and thicker, and metal layer at the bottom, right, the lower metal like metal 1, typically they are smaller in width and thickness. Okay, metal layers on top typically reserved for power, VDD, VSS, and clock. Okay, all right. So now what we are trying to do in this chapter is compute the resistance and capacitance of the wire. Once we compute the resistance and capacitance of the wire, it has to be added to circuit simulation or to our circuit analysis. So then the question is, should we add it like so? Should we have this R and C? And the answer is no, because it will produce an over pessimistic results. What we should do is we should rather divide the wire into n segments and estimate or have a resistance and capacitance for every segment in my simulation or circuit analysis. Well, for simulation, and this might be fine. So say, for example, you divided your wire into 10 segments. You can throw this into circuit simulation and it should be fine. The problem comes though if you are trying to do this in pen and paper or pencil and paper analysis, manual analysis, then this type of modeling, while it is accurate, will complicate your circuit. Okay, so we reserve to a simpler model called the pi model. And basically, the pi model says we place the resistance of the wire between two halves of the capacitance of the wire. This model is referred to as pi model. The pi model is about 3% accurate to fully simulated or fully segmented wire, which is very good results. The T model is actually bad. This is the preferred model for circuit analysis. Okay, so how can we find the resistance and the capacitance of the wire? Okay, so if I have a wire with length L, okay, let me just use a different color, with length L and width of W and thickness of T, then the resistance of this piece of wire is the length of the wire divided by the area, the cross-section area of the wire, which is thickness times W. Thickness times the width. So the width, this is the thickness. Okay, so multiplied by the resistivity, which is a parameter function of the material. Okay, so the resistivity times L time divided by thickness and width of the wire. Because in any process the resistivity of the wire and the thickness of the wire do not change during the design of the circuit, we would like to have this as a constant related to a process. We call this actually sheet resistance. So this is, we refer to it as sheet resistance, and it is ohms per square refer to it. Okay, and then if I want to compute a resistance of any wire, I multiply the sheet resistance times the number of squares, which is actually L divided by W. Okay, so this is basically the interesting part here, that how we estimate the resistance of the wire. Okay, now, so what are um, uh, some of the resistance that we have um, for for um, for different connectors? Well, in older processes, aluminum was the material to create wires. In contemporary processes, we introduced other lower resistance material such as copper. Okay, so you can see that here copper really right on top here with low resistivity compared to aluminum. Okay, but keep in mind that there are other challenges in process that makes one material preferred over the other one. There are uh, issues relates to robustness, issues related to the strength of the metal. So not only resistivity is, and of course the cost as well. Okay, so many factors gets in the way to determine which metal we choose to lay out the wires. Okay, there is an interesting thing here when we estimate wires. These are vias and contact. Vias is really when a wire connects to a wire. So, for example, I have a wire in metal 2 and I need to connect it to a wire in metal 1, and we know these are in different stacks. So I have to have some kind of what we refer to as via. So this has some resistivity that need to be modeled. More interestingly is that when I have metal 1 touches silicon, the surface of the silicon, I have to have something called here contact. Okay, so this is a contact. So this is a via from wire to wire. This is a via, and this is a contact between metal and silicon. Okay, and they have some extra parasitic resistance that we need to account for. Okay, now another interesting issue here is that when we put the metal in the uh, in the um, uh, places that they are supposed to occupy. And say, take for example copper here. Copper need to have some kind of should be surrounded with a low conductivity diffusion barrier. So the copper do not touch the material. We need this low conductivity barrier material. Okay, so what's the problem? Well, the problem is that now W has been reduced. W is no more W. W now is smaller. It is W minus T barrier because I have a T barrier here and a T barrier here. Okay, and even also thickness. We notice that we have a T barrier here and we have on top what we refer to as the dish effect. And the dish effect, it is the our dishing effect. It is um, during polishing, the some of this material is pruned out. So we need to subtract this when we estimate the thickness. So the thickness will be T minus T dish and T barrier. Okay, so this is the thickness here. Okay, so what happens here? Well, what happens if we ignore those? We are not giving the realistic resistance. I'm sorry, and the realistic resistance is higher because notice those when they get smaller and smaller here, we will get higher resistance. That's the realistic resistance. So we need to account for those in our formula, and that's why we have updated our formula. So our formula now is resistivity, right? Right? Resistivity, and our formula now, resistivity times length divided by the updated thickness divided by the updated width of the wire. Okay, so here is an example where we are computing the sheet resistance for 0.22 um, micrometer thick copper wire in 65 nano process, and the resistivity for the copper is 2.2 times 10 to the minus 8 per 8 meter. Now, sheet resistance, what we need is to compute the sheet resistance, and sheet resistance is what? Well, the sheet resistance I know is the length, I'm sorry, it is the resistivity divided by the thickness. So this is the resistivity, rho, divided by the thickness, T. And we get zero point 0.1 ohms per square. Now, in the next point, what he wants is he wants the total resistance, assuming that the W of the wire is 0.125 micrometer and the length of the wire is 1 millimeter. And in this case, I apply this formula here where I multiply the resistivity, okay, so this is the resistivity, times the length, divide by the width, and I get 800 ohms. We would like to remember this number throughout this course, that 1 millimeter of wire has resistance of 800 ohms. You might see this in some of your exams or assignments, so I want you to keep this in mind, unless we assume other numbers and other widths for you in the assignment or the exam. Okay, so we have estimated the wire resistance and the wire. Now it's the time for wire capacitance. So how we estimate wire capacitance? Okay, so let's assume we have a cross section, and this is a wire which is going into the board. And this wire has two neighbors, this neighbor and this neighbor. And also this wire has a neighbor on top and a neighbor on the bottom. The total capacitance for this wire, okay, equals the capacitance with the top, which is right here. Let me change color here. Okay, the capacitance with the top, which is right here. The capacitance with the bottom, okay, which is right here. So it is the capacitance with the bottom And then we have the two adjacent capacitances, okay? The two adjacent capacitances, which covers this one here and this one here. Well, this is an interesting. Why these so many capacitance? Well, the answer is in physics. Physics says that if you have metal adjacent to a metal and between the two of them there is an isolating material, okay, you just created a capacitor. Between the two of them there is a capacitor. That's from physics. Okay, so here I have in my diagram here, this is a metal, and 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 between all of these metals we have capacitances because this is isolation material. Okay, okay. So C total equals the C top plus C bottom, which means the capacitance with the top layer, the capacitance with the bottom layer, plus 2 times the adjacent layers. Okay? All right. Now, so how to estimate a capacitance to bottom or well, in the older days when wires were wide, okay, and this is when W was larger, much larger than thickness, okay, and this is in the old processes. We used to use the estimate of capacitance that we had in physics course, because this the capacitance between this metal and the other metal underneath it or on top equals capacitance equals the epsilon for the dielectric constant for the isolating material times the area divide by the distance, and the distance is between the two metals here, or the thickness of the isolating material. So, and the area here typically is length times width. So the area is length times length, all right. And the dielectric is K times epsilon naught, and epsilon naught for free space, and for silicon dioxide, which is the oscillating material here, is 3.9. That was in the old processes. But we know that in new process, what happens is that this W now is much smaller. We are dealing with wires that look like this. Okay, so the W is much smaller than the thickness, and therefore the estimates for these capacitance are much more complicated than the simple parallel plate model. In fact, we will have to resort to equations like these. Okay, so if I want the capacitance without neighbors, okay, so meaning that I have capacitance either on top or on bottom, this is the equation here. And all these empirical formulas, they have certain error, okay, and because very accurate models requires much more sophisticated equations to estimate the capacitances. For our purpose in this course, we will assume that the wire has a capacitance of 2, oops, let's just use another color here, of 0.2 femtofarad per micrometer. Okay, so we will use this as a given constant. Now compare this to 1 to 2 femtofarad for gate capacitance. We are almost there, meaning that the wire capacitance is very close to, in fact, in recent process, this much worse situation where probably uh, wire capacitances are more dominant. But we will assume for a wire that will have a capacitance wire of 0.2 femtofarad per micrometer. So if I have, for example, a 1 millimeter wire, the capacitance for this wire is 0.2 femtofarad times per 1 micrometer times 1000 micrometer. Why 1000? Because this is 1 milli, and this is equal to 0.2 um, picofarad, okay, for this wire. Okay. Diffusion and polysilicon typically are bad for running wires because they have their capacitances and resistance typically are high. So typically they are avoided. They are avoided for interconnects. Okay, so here is an example. Okay, where I have a a wire. Let's see if I can. Where we have a wire. See, okay. So in this example, what he's asking me to do is he says that he has he has a driver of of size 10x, okay, and this is running. There is a 1 millimeter and 1 millimeter wire to a to a receiver driver, and this receiver driver is 2x. Now, what he's what he wants me to do is to convert this circuit into simple RC circuit. Okay. Well, for this wire, okay. So for this wire, let's see if we could for this wire, I know that for 1 millimeter, okay, the resistance equal 800 ohms, and the capacitance is 0.2 picofarad. Okay, and since I would like to use a pi model, okay, where I have half of the capacitance here, the resistance, okay, so I'm going to have this zero point 0.1 picofarad, zero point 0.1 picofarad, and this is 800, okay, ohms, and this is how I'm going to model this wire. Okay, now, so let's put the wire here. Okay, so 800 ohms, and this is 0.1 picofarad, and this is 0.1 picofarad. Okay, and then this the driver here is 10x. He's telling me assume the resistance for the NMOS or the PMOS is 10k ohm. So 10k ohm is the resistance for these guys. But this is when the size equals 1. But when the size equals 10, I have to divide 10k by 10. Okay, and that means that the resistance for my driver is 10k over 10, which makes it 1000 ohm. Okay, so this is for the driver. Now how about how about the receiver here? Well, he told me that in the question that there is assume every size of this has a zero point 0.1 femtofarad. Okay, so I have this is my regular 1x inverter. Typically I have two, and I have here one. Now, if I have 2x, then I need to multiply this by 2 by 2. Now, why 2x? Because he told me in the question that this is a double the size of unit size. Now, how many I'm seeing in the gate here? Well, I'm seeing 2 plus 2 plus 2 plus 1, and this is equal to 6, 6 units. And he said in the question that assume every unit of those is zero point 0.1. So there is a 6 here times zero point 0.1 picofarad. This is for the gate load. Okay, so this is I will see this in the gate load of the, so what I did in this example, I converted the entire question from two drivers and a wire into just an RC circuit. Okay, we will stop at this point and continue our lecture in the second part of our class, as our lecture. Thank you.